Oscillation is when you have an object moving back and forth around one central point. And if an object vibrates back and forth over the same path, taking the same amount of time for each oscillation, this is called periodic motion. In this video, we're going to be looking at oscillations in springs. And here's the kind of spring we're going to be looking at. We have a frictionless floor. We have a spring attached to the wall, and there's a mass on the end of it. So it can move back and forth like that. All springs have a resting natural length. So if you just left it alone, it would stay here. And when you stretch it or you push it, it tries to bounce back here. The more you stretch it, the harder it's going to yank back. And this force that brings it back to equilibrium is called the restoring force. It has a formula. The restoring force is equal to the spring's stiffness constant K, which is how hard it is to stretch it, multiplied by how far you displaced it from the starting position. And this value of X goes both ways. So if you push it 5 centimeters, then X is 5. If you pull it 5 centimeters away, X is 5. Let's look at why it's called simple harmonic motion. Take Newton's second law, F equals ma, and the restoring force, which is also known as Hooke's law, which is what we just looked at. F equals ma, and it also equals negative kx. So we can rearrange for acceleration. Yeah, acceleration equals this, which we got by dividing m from both sides. Now, why do I do this? Because this tells us about the acceleration of something that's oscillating, specifically our little spring from earlier. This says that acceleration is not constant. It doesn't stay as one value. It depends on x. It depends on how far you pull your spring away. So the further from the center, the more acceleration back toward the center. This is the mathematical evidence that the harder you move your mass, the harder the spring will try to restore it back to equilibrium. And these formulas are all in the free cheat sheet in the description. Let's have a deeper look. I'm going to quickly draw our spring at 4 different time points. So what I've drawn here is 4 stages of a spring bouncing. So first stage, you pull it back as hard as you can with your hand. What's happening here? At maximum stretch, X is equal to the amplitude. What's the amplitude? The amplitude simply means the maximum displacement. So if we graphed the oscillation of an object, it would come out as a wave. The height of the wave, the maximum your object can stretch, the ends of the path that it travels, is the amplitude. So it's just the maximum possible distance from the center. So you stretch it as hard as you can, and then you let go. We're looking at the very instant that you let go. What happens? The spring starts pulling back toward the center. That's a restoring force. The velocity is equal to 0 because you just let go. However, acceleration is the maximum it can be because, remember, acceleration depends on how far you are from the distance. And if we're at the maximum distance possible, acceleration is also at its maximum. The two values are tied together. How about at stage 2? What's going on here? As it flings back toward the left, your velocity increases and your acceleration decreases because you get closer to the center. How about at time point 3? This is when the object is at equilibrium. This is its resting natural length, this red line in the center. This is where the spring was trying to bring it. At equilibrium, X is equal to 0 because displacement is 0. The velocity is at its maximum because when it's flying through the center, it's traveling at full speed. And acceleration is 0. There's 0 restoring force when it's at the center. How about at the final, level 4? This is when it's at its maximum compression state. It's flown all the way over here, and it's fully squashed. It's ready to bounce back. So X is equal to the amplitude again, but on the other side. The velocity slows until it reaches 0 for a very, very brief instant. Just like how in projectile motion, at the peak of a path, velocity is 0. And acceleration builds in the opposite direction. In a system like this, where we're assuming there's no friction, no gravity, no air resistance, no any opposing force, then this back and forth would repeat endlessly. It oscillates forever. Bounces to one end, and then bounces to another end. The key takeaway from this is that acceleration is 0 at the center and the biggest at the ends, and velocity is the other way around. It's the fastest through the center, and at the ends it's momentarily 0. Before we do an example problem, there's one last concept. So this value t represents the time it takes for one full back and forth trip, aka one period. It's called periodic motion. This f value here means frequency. So frequency is the number of cycles per second, and it's measured in hertz. If your spring bounces 2 full times per second, then your frequency is 2 hertz. And your time is 1/2, or 0.5 seconds. That's how long it takes to do one full bounce. What if our spring and our mass is not on a surface? What if it's hanging? That means we're going to have to consider gravity. So here's our spring again. Here's our little mass. The spring will simply stretch down and down from gravity until the restoring force is equal to the pull of gravity. So gravity will pull it down until it's just naturally resting. So if you imagine there's no gravity, then its natural resting length might be here. But then gravity will pull it down to here. But remember, the further away you are from the resting point, the stronger this restoring force. So eventually they will balance. And then this will be the new point of equilibrium for your mass. This will be the new x equals 0 point. Example problem. A 75 kilo dude is standing on a trampoline, and he stands on the trampoline. It stretches down 5 centimeters. We're going to solve for two values. First thing is the spring stiffness constant. The second thing is how far down does it stretch if the dude was 100 kilos. Here's how we're going to go about doing this. Every formula we've looked at in this video is in the free cheat sheet in the description, and it's what we're going to use to solve the problem. The spring stiffness constant is K. And a formula that involves K is Hooke's law, F equals Kx. We can isolate K by dividing both sides by X. So K is equal to force over displacement. Force stretching the trampoline is the weight of the dude, so gravity. So his mass times gravity. The displacement is 5 centimeters. The weight of the dude, let's quickly find that, would be 735 newtons. The displacement in meters, because we want our units to stay consistent. 5 centimeters is equal to 0.05 meters. So that's the two values we're plugging into our formula. Plug it into a calculator. Your answer is 14,700 Newton meters. For the second part of the problem, we're looking for how far the trampoline stretches down when the guy is not 75 kilos, and he's a little heavier, so 100 kilos. We're solving for X. Because it's the same spring, same trampoline. When there's more weight, the stretch should increase proportionally. We're going to use the same formula, which is Hooke's law. This time we're looking for X. So X is equal to F over K this time. We just divided both sides by K. The weight of the guy is given with mg, which is 100 times gravity, which is 980 newtons. So if you remember, our last guy was 735 newtons. Anyway, let's write that. We also know K. We found it in the first problem. It was 14,700. The answer for this is roughly 6.7 centimeters. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.